Intro Stats Review Crash Course Part 2. Okay, shapes of distributions really start to matter when we get into inferential statistics. We want that. We want it to be normal. And a perfectly normal distribution, the mean, median, and mode are identical. When you have real data, identical is very, very, very uncommon. So we're looking for probably close. With a positively skewed data, the tail points to the positive. This is also called a right skew, but I think about it as positively skewed. What that means is that there are some outliers over here on the positive side that are actually pulling the distribution towards it. And what that does is it affects our mean. So you can see the mean score no longer represents center very well. That's a problem. With negatively skewed, it's the opposite. So the tail points to the negative, and again down here, this would be our mean, and it is being pulled over towards the negative side. So we are hoping for normal, or normal enough, and that's the hard part. It's like, what is normal? How do we actually measure that? So there's a new statistic, hopefully not too new for you, called skewness. And you're going to see it in SPSS and in Excel when we get to descriptive stats. We want this value to be between plus and minus 1. There are other ways to talk about statistical skewness. We're just going to talk about if the skewness value is between plus or minus 1, congratulations, we can call it normal enough. Some vocab review. With statistics learning, please start a vocab list. So I first want to start with critical value. So if you think back to your intro stats course, these are those really awful tables that you had to look up in the back of the book or some appendix and find the right table and then find the right value, and it was a critical value, and then you had to compare that to something else. You're welcome. We're not doing that. Instead, we're going to have these calculated values for whatever test we're doing. And we're going to change that value to a p-value. The probability value is then compared to alpha, and alpha completely depends on confidence level. So let's start from the top and go down. Confidence level is how confident we want to be and how much error we're going to allow. So at 95% confidence, my level of significance is 0.05. I'm only allowing 5% error. So if my p-value is lower than 0.05, it is considered significant. At 99% confidence, I'm only allowing 1% error. So my level of significance, my alpha, is 0.01 for 1%. And if my p-value is lower than 0.01, it is considered significant. And that leads us to hypothesis testing. So this is just a procedure that allows us to evaluate some data and see if we can generalize to population. So we're trying to take the sample statistics and estimate things about population parameters. It is always based on a research question, and these are set up before you even start the study. Because what we're trying to do is find significant differences. So there's a difference between the green and the blue distributions. They're not on top of each other, they're different. And the mean score for the green, let's just say that right here is 50 and the blue right here is 65. So they're different distributions. The means are different. But we want to know, are they significantly different? Or did we just happen to sample slightly low and slightly high in the same distribution? So we could draw a line and be like, oh, these are actually part of the same distribution. This data set's just slightly lower, this distribution is just slightly higher, but they're really part of the same distribution. That's what we're doing when we start talking about statistically significant. And by the way, don't use the word significant in my class unless there is a p-value attached. If you're trying to say that something is important, use the word important, not significant. Because this is a technical term. And I will also say that it may not be the same as practical significance. So we'll get into effect size analysis for practical significance, because large samples tend to yield statistically significant differences, but that doesn't mean it's always really useful to practice. For example, when I was in middle school, we saw differences between guys and girls on math scores. But let's just pretend that the difference is only 2 points. So there's only 2% difference between guys and girls. It's unfortunate. I'm definitely going to work on my females with math scores, but I'm not going to change my entire teaching practice for 2 points. On the flip side, our underrepresented minorities are scoring whole grade levels below on their math scores. That is a drastic difference. That is a massive effect size, because the difference between the two groups is very, very, very different. So that makes me want to change my entire practice and focus really hard on my underrepresented minorities to get their math scores up. When we're talking about hypothesis testing, we have 2 choices, the null and the alternative. The null hypothesis says null, nada, nothing. Nothing is different. Everything is the same. There's no relationship. There's no association. There's no difference. Everything is the same. The entire statistical tests that we talk about are based on the assumption that the null hypothesis is true. Therefore, we have to show evidence that the null hypothesis is not true so that we can reject it and support the alternative. We never accept anything, and we're never trying to prove anything. We're just trying to see, can we reject this idea and support something else? Like the research hypothesis. This is also called the alternative hypothesis. Typically, this says there is a difference, there is a relationship, there is an association. These can be one-directional or two-directional, if you remember from intro stats. Luckily for you, pretty much everything we do is going to be just assumed to be two-tail, and we don't care who's higher. So we don't care if males score higher or females score higher. We just want to know, is there a difference? So think back to your last science class, and I want you to pause the video for just a second and write out what the scientific method is. So pause the video, write out the scientific method. I'm hoping that you started with observe. Most people skip this and go straight to research question. But we don't have a question if we don't observe something that makes us curious about something. And that question leads us to a hypothesis. So we think it could be this, or we think it could be this. And we collect data to see which hypothesis is supported. We analyze it somehow, and we come to a conclusion. And we say, okay, was it this hypothesis or this hypothesis? And that leads us to a decision on what to do. So we asked a question for a reason. Hopefully that leads us to some sort of an action by the end. And usually that leads us to new research questions. It's the exact way that inferential stats works. It operates under the same system. So we have a question, we state some hypotheses, we establish how confident we want to be, how much error we're going to allow. Typically 95% is all we need in social sciences. We could be more confident in 99% if it's high stakes. All medical studies are 99, if not 99%, 99.9% confident. But if we get into the business world, sometimes they're cool with 85% confidence. They don't care if there's 20% error. If it works 80% of the time, they're happy. And then we have to choose the test that is appropriate for what we're trying to understand. And that's going to be what we learn in this class. Chi-square, t-test, ANOVAs, regressions. What are we trying to do? We calculate that, and by we, I mean SPSS. And then we compare that p-value to our alpha, figure out if it's significant or not, and then we move forward. Of course, we could be wrong, and we will probably never know. That's what's so scary about error, is that we may never know. But there's a type 1 and a type 2 error. So here's how this works. If I reject the null hypothesis, so I find a difference in my data between guys and girls on their math score, when in reality, in real life, there's no differences. We just happen to sample maybe high or low, something happened with our data sets. we found a difference when in reality there is no difference. That's a type 1 error. And that's scary because if we found a difference and we publish that, people are making decisions, changing practice, changing policy on things that aren't true. My dogs always have to make an appearance. Okay, so a type 2 error would be that we failed to reject the null. So we could not find a difference in our data for whatever reason. And in reality, there are differences in real life. We just didn't find them with our data. That's a type 2 error. Those are really, really unfortunate, but we're not changing policies or practice for not finding something. And typically, these don't even get published. If you really, really think there's a difference, a lot of times you can collect more data or potentially better data or different variable proxies, and you will likely find the difference that you were looking for. But we're not changing anything. So a type 1 error is more scary because we're changing things and changing practice, and a type 2 error is not. Here's the deal. That could be a research design issue. It could be a variable choice issue, a measurement issue. It does not tend to be a statistical miscalculation. It tends to be based on the whole entire study. So you have to have your study solid from start to finish. Okay, so let's go back to that green and blue distribution. So we have a mean of group A is 50 and the mean of group B is 65. And we want to know, are they different? Well, I mean, 50 and 65 are different, but are they significantly different? So I run a t-test and I get the answer of 2.1. Is that significant? Well, if you remember, the cutoff value is 1.96, which most of you probably don't have memorized. Is that significant? Well, I don't know. Change it to a p-value. It's easier. So I have a p-value of 0.04. Is that significant? Well, we still don't know because it depends on what alpha we're using. So if we're 95% confident, then yes, 0.04 is less than 0.05. We have a significant difference between those two distributions. But at 99% confident, only allowing for 1% error, 0.04 is larger than 0.01, so it is not significant, and we say that those two groups are part of the same distribution and there's no difference. That's what we're trying to do here. This entire thing is under this theoretical distribution. We'll talk more about this when we get to Stats Theory Week. But if our value falls here, so if our value, that would be that 2.1 for the t-test. If it falls here, there is a high probability that the null hypothesis is true, meaning there is no difference, there's no association, there's no relationship. But if our value falls over here on the edges, there's an extremely low chance that the null hypothesis is true, and hence we are going to reject the null hypothesis in support of the alternative. I know it is a lot of backwards thinking and a backwards way of talking. You'll get used to it. So we're trying to reject the null hypothesis to say that there is a difference, there is a relationship, there is an association, but we don't have a lot of room to find it because the entire thing that we are doing, the entire statistic, is based on the probability, is based on the null being true. And so we have to be able to be on these edges to reject the idea that the null hypothesis is true in support of our alternative hypotheses. Think about it this way. If I cut this picture apart, this little puzzle piece is very, very small compared to this entire puzzle piece. In fact, this entire gray would be 95% of the area, and this would be the 5% on the tails. That would be at 95% confidence. These tails would be our 5% that we're trying to be able to find significance based on. Okay, I know this was a lot. You're probably going to want to watch these videos a couple of times if needed, but I promise you got this.